Hello guys and welcome back. In this lecture we're going to start our journey in introducing all of these electronics and embedded systems. Everything is going to start with this little bit of story, the story of the bit. So let us get started. Assume we have one power source, which is a battery, and we have one lamp. If we connect these two directly, well, this lamp will just light immediately, as long as we have enough energy in the power source. So this small, let's call it circuit, has no control at all. So you just like connect the two wires to the lamp and it's going to turn on. Nothing special here. Now let us like add some kind of control to this light bulb right here. So by adding a switch right here, if we turn it on and off like that, we're going to be able to control when to turn on and off the lamp. So if you open the switch, the lamp will be off. If you close the switch, the lamp is going to be on. So this is like the most basic form of a control circuit. It's just a small switch. And I'm gonna call this small switch is a bit. So if my bit is set to 0, like in this case, well, my lamp is going to be set to 0, meaning it's turned off. And now if my switch is closed, so it is set to 1, then my lamp is going to be set as well to 1. Now let us complicate this circuit a little bit. So let us have two switches that will try to control this bulb. Now, this is a two-way series switch. I mean, why do we call it series? Because both switches right here are consecutive to each other. So, by closing one switch, well, the circuit is still open and I won't be able to light the bulb. So in circuits, there is one rule of thumb. I need a closed circuit in order to turn on anything. If I close both of these switches, I'm going to have a current flow and this bit right here is going to be lit. There is another topology of control. Now, let us assume that I have two parallel switches. So maybe I want to control this lamp from two different places. So this is a different type of control. If I turn it on from this side, well, I'm going to have a closed circuit on this path, right? And the light is going to be lit. But if I turn it on from the other side, it's going to be also lit because, well, I have another path for the current to flow. I can also turn both of these on, and what's going to happen is I'm going to be able to light this bulb from both places at the same time. Unlike the series right here, this creates some dependency. So switch 1 right here cannot be conducting unless switch 2 is conducting, right? So this needs to be closed in order for this to close and also conduct current. So this is the most basic form of control logic. Now let us agree on some terminology. When we close the switch, it means that it is 1. When we open the switch, it means it's 0. So this 1 and 0 are the bit we are talking about. Now, they found out that they can do a lot of stuff with this simple logic, and they decided to call such type of switching as the AND gate. It's called AND because you need A and B to be on in order to conduct or get a logic at the output. So I'm going to call these switches inputs, and this is my output. Input is anything that I manipulate at the input of the circuit in order to create some result at the output, which is the lamp. So this is what we call a truth table in the logic design. So we have switch inputs A and B, which are switches A and B. If A is 0 and B is 0, as we agreed 0 means open, well, the output Z is going to be 0, right? Because, well, there is no current flowing. Now, the same thing when A is 0 and B is 1, well, same, I'm going to get a 0 because I need both of them to be closed in order to conduct anything. So the only case that I get an output of 1 is when input A is 1 and input B is 1. If this is 1 and this is 1, it means both are closed, then I will have an output right here. Now, this is the AND gate. We call it AND gate. Now, here we have the OR gate. It means if this switch or this switch are on, I'm going to get an output right here. So, as you can see at the input here, if A is 0 and B is 0, meaning both are open, well, of course, I don't have any current at the lamp. Now, if I have B1, meaning B is closed, well, I'm going to have a path here, so this is going to turn on. Same thing when A is 1 and B is 0, also I'm going to get a 1. And also when I have both of them closed, then I'm going to get an output at the light bulb, right? So we're going to start this small and we're going to build to understand how a whole microprocessor works just by studying these small examples. We're going to build up and we're going to see how will this work. See you in the next lecture. Now let us continue where we have left. We're going to introduce the transistor. I'm not going to go deep in transistors at all right now, but I just want to tell you that this transistor is the same as the switch we were studying. And to sum it up really quickly, if you connect a battery at B, then C and E are going to act like a closed switch. If you remove the battery at B, well, then C and E are going to act as an open switch. So you connect a battery, C and E are connected. You remove the battery, C and E are disconnected like an open switch. As simple as that. Now, I'm not going to go deep in this topology as well, but when you connect the transistors in a certain way, you're going to get gates, the same ones as we have studied, the AND and the OR. Now, this symbol right here is the OR gate. So whenever you see this symbol, if you go deep inside it, you're going to see something like that. Electronics or transistors are connected with each other with this form right here. Same thing at the end. Whenever you see this symbol, this is an AND gate, which is the same as two switches in series together. If you go inside it and take a look, you're going to get a topology that looks like this or similar to this. So this is a black box encapsulating this type of logic for the OR and here for the AND. Now, we're going to build up and see how these ANDs and ORs form everything you know and everything about embedded systems, because everything is going to start from this simple transistor and then combining a bunch of transistors together to create gates like those, and then multiple gates together are going to form different type of electronics component. So see how the picture is getting bigger and bigger right now? Now in the next lecture, we're going to see how this picture is going to form our embedded systems. Now I want to continue building up and introduce the binary system. Binary is something like a 1 or 0. We have already introduced a bit, which is a 1 or 0, and this is what binary is actually. It's nothing more than something is on or something is off. That is what is binary. So they figured out that if they can create some kind of arithmetic to this ones or zeros, maybe they can create something like a calculator, right? So they invented the binary system, and then they tried to get this binary system and implement it in digital circuits, in gates like the AND gate and the OR gate. And by putting this bunch of transistors together, they're going to get some useful devices. Now, the numbers you have in the binary systems is just 0 and 1. You have nothing more than that. So let us put all the operations that we can do with these 2 bits. If we have 0 plus 0, well, they said, okay, the sum is going to be 0. If they put 1 plus 0, well, they're going to get something like just 1. And that makes sense. Now they said, okay, what if we have 1 plus 1? They said, okay, the thing here is going to be 0, and we have 1 as a carry. It's the same thing as adding 9 and 1. We're going to get 10, which is 1, 0, which is repeating the whole system from 0 to 9 one more time. Same thing here, because the numbers here are 0, 1, right? In the decimal, you have from 0 to 9. So when the 9 finishes, well, you're going to start over and roll over, and then you're going to get 1, 0, which is 10. But here, well, whenever you add 1 plus 1, you're going to roll over again, which is 0, and you're going to put 1 next to it. So you can say 1 plus 1 is actually 10. This is how the binary system works actually. You just have these three operations. 0 plus 0 is 0, 1 plus 0 is 1, 1 plus 1 is 10. As simple as that. It's not really 10, it's just 0 and 1 in the carry. We're going to see what does this mean later. So they thought, okay, let's design some circuit that looks like this. I'm going to have two bits right here, two switches. I'm going to have a bunch of AND and OR gates connected together, and there is a result at the output and a carry. So they said, okay, if I put 0 plus 0, I want to get a 0 here. If I put 1 plus 0, I want to get a 1 here. If I say 1 plus 1, I want to get 1 here, and I want to get 1 in the carry. As simple as that. Now, this is the representation for this, and they called it half adder. We're going to see later why it's not called full adder, but an half adder, because it's only summing 2 bits right here. So, this is the black box representation. You just have a box with 2 bits, but we don't know what's inside. Now there's another representation, which is we're going to see how it looks like if we put AND, XOR gates, and OR gates, NOR gates. There is many types of gates which we're going to introduce later. Here we have an XOR gate and an AND gate. If we connect them together, we're going to get a half adder. So here, 0 plus 0, you're going to get a 0, and here you're going to get a 0. 0 plus 1 or 1 plus 0, you're going to get a 1 here and a 0 here. This is the carry. And this is the z or the sum, same thing. If you have a 1 here and a 1 here, well, you're going to get 1 here and 1 here. So we are summing now in the binary system, and that's great. That's a huge progress. Now we can create a lot of arithmetic and a lot of mathematics just using this simple circuit. Now, if we open up this, if we open it up and see what the electronics looks inside it, we're going to see transistors that are connected in this way. So this side right here, the S, looks like this. This is the sum, this is the A and the B. Same thing here. If you look at the carry, its circuit looks like this, right? So right here, if we have some electronics and we connect it exactly like that, and we have an inputs A and B, well, you're going to be having like an adder, a circuit adder, which can later be represented to create a real calculator, which is the basis of the CPU. We're going to see that also later. As you can see here, there's a bunch of inputs like A hat, B hat, B. So don't get yourself confused. We're not going to talk about this level here, but it's really not that complicated. It's just that you get all the A's and connected them together, all the A hats and connect them together to one terminal, B and B hats as well separately, each to a terminal, and then you execute them in a certain way and you just get this half adder. And that's, as I said, a huge invention, because you're starting with simple switches, you then turn them to a transistor. You turn these transistors to some kind of logic gate, and then you represented some binary system, and you combine these together, and now you have something that can do real math for you. Now, next is we can do the same thing for subtraction, for multiplication, for division. We can create circuits that do this exact job. So if we have all of these operation and we have these 4 boxes right here, well, we can do any operation in math we want, at least as a binary operations. That's huge. Now, if we multiplex all of these together, the multiplication, addition, the subtraction, the division, we multiplex all of these circuits together, and here we have some operation input. Like we say, okay, if I insert some 0 here, I want you to perform an addition. If I insert a 1 here, I want you to perform a multiplication. Let's assume that this op has 2 wires. If you put 0 here and 1 here, maybe you will be able to perform division. If you put 1 here and 1 on the other op wire, then you will be able to perform some other mathematical operation. So by multiplexing these circuits together, you have something called arithmetical logic unit, or an ALU. This is the basis of a CPU. Now your computer has a CPU. Any electronic device has some kind of microcontroller or CPU which has this ALU. Your calculator has an ALU. So as you can see from simple switches, you can create a whole mathematical logic calculator right here. Now we are building up, as you can see, and later we're going to see more stuff and we're going to connect them until we have a full embedded system. Now let us move these logic gates one level further. Now let us build up and see where we can go with all of these logic circuits. Now we're going to see how we can store numbers using those ANDs and ORs. Actually, if you connect these two ANDs like this, these two NOR gates, which we're going to see later like this, you're going to get a storage circuit. So if you put one right here and a 1 on this CLK or clock, you're going to store 1 right here all the time. Now, if you change here to 1 or 0, it doesn't even matter. This 1 that you put in the first place is going to be stored right here all the time. So like that, you have created some type of storage, right? So all I'm saying is, if you connect a battery between clock and D right here, okay? So all I'm saying is that if you get battery, you connect D and clock to it, you're going to get a high voltage right here or a 1 on here. Like if you put a lamp, you're going to see it light if you connect it right here, okay? So now if you remove this battery from here, you're going to see that the light is still on. Well, this does not mean that there is no other energy sources in this circuit. No. All I'm saying is that at the input, if you remove this battery, just at the input, well, you're going to have no effect at what the circuit here is storing. So right now, by doing this type of circuit, well, you're going to store zeros and ones just by whatever you put at the D. If you put a 0, where you're going to see a 0 here. If you put a 1, you're going to see a 1 here. And again, that's just great because like that you have created a storage unit. And we're going to call this circuit a D flip-flop. And this is almost the most basic storage unit you could have. Now this is the black box representation of this D flip-flop. I don't want you to worry about the internal functionality yet for this D flip-flop. We're going to see that when we get into FPGAs. But I just want you to see that in the logic gate representation right here, that just a bunch of ANDs and ORs together, NORs and other gates, are going to form what's called a storage unit. So all of these are just switches actually. So switches can actually, if you connect them in a certain way, can give you this type of logic. And this is what it looks like if you connect it using CMOS or transistors. CMOS is just a type of transistor, and if you connect them in this topology, well, this is the D, this is the clock, and here we have the Q and the Q hat. If you excite these inputs with batteries or with voltage, well, what you're going to get is a storage unit. So how can we build a memory with that? Well, if we put multiple of these D flip-flops together, we can create something called a register file, because we call this D flip-flop a register because it's registering bits, 0 and 1s. If you put them together, you're going to get a register file, and a register file is some form of a RAM memory. I know the topology could be different in the transistor level, but if you are unable to imagine what is a storage, it's nothing but these electronics connected together like that in order to store bits, zeros and ones. So we are still consistent. If we have switches, we can create memories, we can create ALUs in order to perform arithmetics. So now we can perform arithmetics, we can store it, and that is the basis of a calculator. It contains a small memory and an ALU, and that's it. So in FPGAs, as we're going to see, we're going to be able to build a calculator, we're going to be able to build a small microcontroller. We're going to see all of this later in this course. Now, in the next lecture, I'm going to talk to you about GPUs and what is the basis of a GPU. Now, in order for us to understand the story of a GPU, we need to understand display, because GPU is responsible for display most of the time. So let us get started. In order to represent display, we're going to represent multiple lamps right here. Remember this circuit where we have a power source, a switch, and a lamp? Well, assume that we have a matrix of that. And well, whenever we turn on some of these switches, the lamps are going to turn on. And this is exactly what a display is. It is multiple lighting units that are set together like that. And if you light it in a certain pattern, you're going to see patterns on the screen, right? So if you change the pattern, whatever on the screen is going to change. Now, you can think of it as these rolling screens that display text. So you have a fixed size screen, and all that is happening is that the light units are changing locations in order to give you the illusion that the text is actually wrapping, right? This is what a display screen looks like. The same thing with your laptop. Your laptop is also consists of a lot of these lighting units, and they are being turned on and off with a certain control unit in order to display what you're seeing right now. So this is the concept of a screen. Assume that you have a screen with these dimensions right here. It means that you have 1080 horizontal lighting unit and 960 vertical lighting units. And they are forming a matrix of lighting units, and they are changing patterns in order to see what you're seeing on the screen. This is oversimplifying what a screen is, but actually this is the concept. This is what it is all about. This is where it all started. So now let us see how a screen can display anything at all. So remember our register or the D flip-flop we have talked about? Well, imagine that we have this storing unit and we have stored some stuff in these, right? Well, and every storing unit is connected to a lamp. So if this unit is storing a 1, this lamp is going to be turned on. If this is storing nothing, well, this will be turned off. So if this is storing a voltage, it means that this will turn on. If this is storing no voltage, then there's no voltage to turn this on, right? So a screen is actually a giant memory or a giant register file. Assume that we have a lot of these D flip-flops and a lot of these lighting units. And whatever we store in these D flip-flops, we're going to see it on the screen. This is why every display device needs some kind of memory, right? Because the memory is actually the frame you are seeing. Everything is stored in this memory is going to reflect the frame you are seeing on the LEDs. It's actually not like that literally, but this is the basic concept of display. So if you have a 200 by 200 screen, you're going to have a 200 by 200 flip-flops and a 200 by 200 lighting unit connected to each flip-flop. And then whatever you store in here, you're going to see it on the light bulbs, which will give you the illusion that you're seeing shapes, numbers, or whatever you're seeing on the screen. You're going to form letters, you're going to form images, or just by changing what you are storing in this storing units. Now, let us see what is the role of CPU or a GPU in display. In order to change what we're seeing here in display, we need to change the content of the memory, right? We have said that there is a flip-flop mapping to every one of these lights. So we have flip-flop here, light here, flip-flop here, light here, and so on and so forth. So in order to change the display, we need to change the content of the memory, okay? The device that changes this is actually the ALU. So the ALU is going to write data to this memory, right? So assume that you want to shift everything by 1 right here. You're going to let the ALU perform some mathematical operation, and it's going to change the memory content here, and you're going to see this right here shift by 1 unit, right? So you change the memory, the display is going to change, but in order to change the memory, you might need to create some mathematical operation, let's say, in order to change it. Now, changing all of this by one ALU takes time, right? Because this ALU need to access and change result for every flip-flop you have. And this takes a lot of time. Because imagine that you have 10,000 flip-flop here and one ALU. So the ALU is going to perform operation on flip-flop 1, 2, 3, 4, 5, and until you reach 10,000, right? That's a lot of operations. But if you have multiple ALUs, every ALU can be responsible for a chunk of this memory, and it can change its content. So instead of changing one flip-flop at a time, we can change 9 flip-flops at a time. So this chunk of ALU is responsible for this one is responsible for this one, and so on and so forth. So you put multiple ALUs together, they change multiple places in the memory, and by that you change the display. Again, the process is much more complicated than that, but this is the basic concept. Now, this multiple ALUs is actually a GPU. A CPU usually contains just a very few numbers of ALU, but a GPU contains a lot and a vast number of ALUs that are packed together in order to perform faster operations. That's why your display needs something fast, especially if you are doing some 3D manipulation, some 3D design. You have a lot of chunks in the memory that you need to change a lot, and you need to do a lot of mathematical operation in order to do rotation in 3D, rotation in 2D. Well, this needs a lot of ALUs. This is why a GPU is much faster to perform these applications. That's why if you are playing a game and the game has a lot of powerful graphics, if you play it on a CPU, the CPU cannot change the memory so fast, so that you're going to see a lot of lag in the display, right? You're going to see the game lagging and stuff, and that's really annoying. But if you have a powerful GPU, well, the memory content will change faster, meaning the mathematical operations are being done faster, meaning the display is smooth. And this is the basis of memory, CPU, GPU. This is the basis of all the electronics you're seeing around you right now. And I wanted to start with this introduction in order to tell you that embedded systems are similar to each other. And if you understand these concepts, you can work on any electronic system you really want. And we're going to demonstrate a lot of electronic applications right now. When we start with the FPGA section, with the Arduino section, ESP32 or a not MCU section, we're going to see all of these later. Now in the next lecture, I'm going to compare to you the different embedded systems we have. Now in this lecture, we're going to start distinguishing the different type of industrial embedded systems that are in the market. There are a lot of embedded systems in the market. There are hundreds and thousands of electronic boards that you can see and you can use, but there is some distinguishable categories that we're going to notice. So the most common the top 5 embedded systems we can see in the market are FPGAs, Arduinos, not MCUs, Raspberry Pis, and PLC. Of course, there are other type of microcontrollers, industrial microcontrollers, but those are the best way to start with this domain. I mean, if you can master these, I can assure you, you can get a job anywhere, or you can start your own company in embedded systems. Now, we're going to start talking about these one by one. We're going to start with FPGAs specifically. So it looks like a regular embedded system board, does not look like anything special, but it's the only device that you can design your own ALUs, memory, logic gates, just by drawing those circuits and programming those circuits. So you can create your own processor, you can create your own GPU, you can create your own ALU, and just put it on this chip. That's a huge revolution, because instead of buying a microcontroller, you can create your own microcontroller inside this FPGA. Or let's assume that you need multiple ALU slices, or you need some accelerator for your hardware. The best way to do that is by programming your own FPGA. And the FPGA industry is really huge in any kind of electronic application, especially the military application. I mean, usually when any electronic system designer is trying to design a new system, they prototype using an FPGA, because instead of going and building this customized chip, well, and it costs like hundred thousands of dollars, you can just prototype it and draw your own circuit and just burn it on this board. They use special languages called VHDL. Another one is called Verilog. There's also System Verilog, System C. All of these languages can be used to program FPGA, but the most common ones are VHDL and Verilog. I mean, do you remember our a half adder that contained an XOR and an AND gate, and it can sum up bits together. Well, we could program it just like that and then burn it here, and this whole embedded board is going to turn into a half adder. We can combine half adders together, we can combine memories and stuff, and we can create a full customized microcontroller on this. And I'm going to dedicate a whole section on this new technology, which is called FPGA. It might sound like something new to you, even if you are in the embedded systems industry. I mean, even the embedded system industry don't know a lot about FPGAs. That's why I want to build a concrete background for you so that you can understand FPGAs, because if you understand it, actually you can understand any microcontrollers, because any microcontroller is created by customized FPGAs like those. I mean, you prototype your microcontroller on here, and then you go and manufacture uh, a microcontroller chip like the Arduino's one. I mean, you could design a whole Arduino hardware inside this chip and use this board as an Arduino. And Arduino actually is the brand name for the ATmega 32 microcontroller. So right now, let us jump to the Arduino. In order to understand an Arduino, we need to understand an 8-bit microcontroller, because the Arduino is nothing but an ATmega 32 microcontroller. So a microcontroller contains an ALU, a memory, a GPIO, and a flash. We have talked about RAMs, we have talked about ALUs, but we did not talk about flash and GPIO. Actually, a flash is very similar to the RAM. It's a memory, type of memory, a much faster one. But what we do here is we store our program. I mean, I'm going to give you a very simple example. If you go back to this FPGA, see this code? This code is going to be stored in some kind of flash. So right here for Arduino, when you type your C program, Arduino program, you're going to store it in the flash, and then it's going to send instructions to ALU to do operations like to store bytes, to store bits, to perform GPIOs. GPIOs actually are those pins that you see here. Let's go back. See all of these pins right here? These IOs 0, 1, 2, 3. You can read from sensors and you can activate motors and lamps using these IOs. This IO bridge here and IO bridge here. Same thing here. The FPGA contains IO bridges here and here in order to communicate with other sensors and actuators. So, an Arduino basically contains a flash, ALU, RAM, and GPIO. And any microcontroller actually contains by the bare minimum 4 modules right here. So you write a program, it's executed in ALU. If you need to store some stuff, it's going to be stored in the RAM. If you're going to activate some motor or lamp, it's going to be through these GPIOs. So as we can see, the basic difference between an FPGA and an Arduino, FPGA is a customized hardware where you can design your own hardware and create it on a chip. An Arduino is an already designed hardware, so it already contains an ALU, a RAM, a GPIO, and a flash. And all you can do is program this flash in order to use these GPIOs and ALU in order to, let's say, activate motors and read sensors. So the basic difference is what I just said. In FPGA, I could replicate all of these things multiple times. I mean, I could create this same architecture, but I could create multiple ALUs, burn it on an FPGA, and I could have my own microcontroller on an FPGA. Now let's just jump briefly to Raspberry Pi. It's much more powerful in terms of CPU, it has a larger memory, but it also contains a GPU. This is what makes it powerful. Raspberry Pi is actually different from Arduino, even though it has a fixed architecture, same as any microcontroller like Arduino, but it still could be much more powerful because it can run an OS. It can run an operating system. Now, an Arduino cannot run an operating system. In Arduino, all you can do is just have your program on flash and let it execute. But here, stuff are a little bit more complicated. And we're not going to go into the complication of the hardware of the Raspberry Pi because it's a little bit on another level. You need to understand threading, you need to understand multi-cores, you need to understand parallel design. There's a lot of stuff that need to be understood before we can understand the whole architecture. But I just summed it up to you briefly. You have a flash, ALU, GPU, RAM, and GPIO. This is all you need to know about the fixed architecture of the Raspberry Pi. And the CPU here, which is the ALU, is much more powerful than the one on the Arduino. So is the RAM, it's much larger. Additional thing, Raspberry Pi contains a Wi-Fi module so that you can connect to your router and then you can connect to multiple wireless devices. Now let us get into Note MCU. The Note MCU is very similar to the Arduino architecture, but it's a little bit more powerful in terms of RAM and flash, and it also contains a Wi-Fi module. It has a flash where you can write your program and let it execute, but it is mainly used for IoT projects. And we're going to get deeper into that right now. I just want you to understand right now that Note MCU and Arduino are very similar. The only difference is that it has Wi-Fi where you can communicate with other devices. And it's much less powerful than a Raspberry Pi because the Raspberry Pi contains a GPU, it runs an OS or an operating system, but here you just write instructions or a program and you let it execute. Again, in Raspberry Pi, you have something like Linux or Windows where you can write your own Python programs, C programs, C++. You can open internet, so it's not really about writing a program and let it execute. It's much more complex than that. So, this is Node MCU. We have talked about FPGAs, Node MCU, Arduinos, and Raspberry Pis. Now, let us talk about the last bit here, which is the PLC. A PLC could be something similar to Arduino, or it could be something similar to Raspberry Pi. It depends on the hardware architecture. A PLC actually is used in factories when you need to control a whole machine, when you need to control some production line, you use a PLC because a PLC is much more robust and much more reliable in sensitive and dangerous applications. Let's say that you have a nuclear reactor. A nuclear reactor has some sensors, it has a lot of chemical actuators. All of this sensitive stuff needs some reliable microcontroller that guarantees that it won't fail in the middle of operation, causing a disaster. So a PLC is much larger in size and it is much more robust and reliable than regular microcontrollers. So it's more concerned about safety. Now, as I said, it could have an Arduino architecture where you have a simple flash, RAM, ALU, or it could have something like Raspberry Pi where you could run a whole operating system on it and design a lot of projects on PLC throughout this course. Additionally, it contains interfaces for bus communication. And this industrial bus communication, like Modbus, let's say, like Profinet, Profibus, they are used to connect with industrial sensors that are used in factories and production lines. Now, this is a very brief introduction, and I just wanted you to see the difference between these devices and what kind of architecture it could have. In the next upcoming lecture, we're going to go into details of the operation of every single device we have talked about. We're going to run projects, we're going to design some really cool stuff, so just stay tuned and follow me along this great, wonderful course that is going to create some really solid background about embedded systems and electronics world in general.